I guess it's 3:30, we can get started. Thanks for coming. If you like tweeting or you're going to be tweeting this session, they ask that you tweet on the standard VMware infrastructure Twitter handle. But also if you could add the 1196 as the tag so that I can keep track of it. So standard disclaimer, I'm supposed to leave this up for a few minutes at least so that you can read it and know that everything I'm telling you probably isn't true or might not be included in the product. As an agenda, what we're going to be talking about mainly is I'm going to go through a refresher of vCloud Director networking, talk about some new features that we have, either new or old, and what's changed in them, do a deep dive on the networking, and then I'll go into some details on VXLAN. So as part of a refresher, this is the big picture in vCloud Director networking. You have an external network that provides external connectivity, and then org networks and vApp networks. So when you think of vCloud Director networking, it'll come in 3 different layers: external networks, org networks, and vApp networks. When you think of external networks, this is what gives vCloud Director connectivity to the outside world or to the physical world, the VLAN-based networking. The way it's done is you create pod groups within vCenter, and those are consumed or mapped inside vCloud Director as external networks. When you think of organization networks, these are wholly contained within organizations. In other words, if you have virtual machines that are attached to organizational networks in one organization, they do not span multiple organizations. They provide connectivity primarily to virtual machines and vApps within an organization, and they are backed by network pools. And I'll give you a few more details on what network pools are a little later. vApp networks, on the other hand, are contained completely within a vApp, and they give virtual machines within a vApp definition connectivity to each other. And you can have multiple layers of vApp networking within a vApp. They are usually attached to organizational networks so that you can have your vApps communicate with each other. If you don't connect a vApp network to an org network, you don't have connectivity to the outside organization. And they're also backed by network pools. So when you take an organizational network, there's a number of ways that you can attach it or you can configure it. You can either have it public, which means it's directly attached to an external network. You can have it private routed, which means that you would put in a vShield edge in between it and the external network to provide NAT services or other networking services. Or you can have it privately or private internal, which means it has no connectivity to the outside world. It'll still give vApps ability to talk to each other, but they won't be able to talk to the outside world. vApp networks are inherently private, meaning that when you create a vApp network, by default, it has no connectivity to the outside world. And the main purpose of it, like I said, was to give virtual machines within the vApp the ability to communicate with each other. The vApp networks can be connected to org networks, but they cannot be connected to external networks. And the reason for that is the vApp networks, like I said, the networks within vCloud Director come in multiple layers. And the only way you can connect a vApp network is to an org network. There are 3 methods that you can use to connect to an org network. It can either be public direct, which means you've attached it directly to the org network. It can be private routed, like the organizational network, in which case you've stuck a vShield edge between the vApp network and the organizational network. And they can be fenced. And in fenced mode, it's a special or unique version of private routed, in that you're using the vShield edge to provide proxy app services for you. What that allows you is the capability of having duplicate MAC addresses within your environment. So you can have a catalog entry within vCloud Director for an application. You can then check that application out and duplicate it within your development environment, for instance, and have exactly the same configuration within that vApp. The vShield edge will provide proxy app services for other machines on the same layer 2 network that your inside machines are on. Oh, and by the way, I was told if you have questions, you need to stand by the mic so everybody else can hear them. But feel free to interrupt during the session. I think we have enough time to answer questions during the session as well as at the end. vShield Manager is the appliance that's deployed within the vCloud environment, and it provides the firewallings or configurations for the edge firewalls. It'll manage those, it'll maintain the configurations, and it'll be able to push out and execute new edge firewalls as needed. If an edge has an issue and it needs to be replaced, it'll be deleted and a new one will be deployed. Since vShield Manager has the configurations already, it'll push out new configurations for the vShield Edge. It's also responsible for managing all the configurations, maintaining them, and there's options within the UI for backing up the configurations that are built into the database of the vShield Manager. If you need to interact with the vShield Manager, you can either do it through the web GUI that's provided for it or through the REST APIs. The vShield Edge, on the other hand, is the security virtual appliance. It's a virtual machine that's deployed by the vShield Manager, and it provides networking and security functions for the networks that you have. Some of the networking services that it has are things like DHCP, NAT servicing, and load balancing. In terms of security, it will do the 5-tuple firewalls for you, as well as the VPN. And for VPN, it will now handle IPsec as well as SSL VPNs. So network pools. Network pools, from a VCD point of view, are pre-configured networking resources. And what that means is that you have network resources that are available to be consumed by tenants within the vCloud Director environment. You can think of these as, in a hosted environment in a physical world, the service provider might have a closet full of switches. Anytime a tenant needs a new network to run their application on, the service provider will go into this closet, pick up a switch, hand it to them, and give them the capability of attaching virtual machines to them. So when you're configuring an organization network pool, you'll usually assign a fixed number of networks that they're capable of providing. What that would be equivalent to is telling them, okay, like you can create networks, but you can only create 10 of them, and I'm setting aside 10 switches for you. So after you've consumed those 10 switches, you can't create any more networks. And that's the limitation you have on you can impose on the networking pools. So the types of network pools that you have are currently 3, or there used to be 3. You could have pod group backed, you could have VLAN backed, and you could have vCDNI backed, or vCloud network isolation backed. And I'll go into a few more details into those. So the new cool features that are out. Currently, if you remember the first picture I showed you of the big picture, you had an edge with 2 interfaces only. The vShield Edge now is a multi-interface capable firewall, which gives you a lot more capabilities in terms of how many networks you can attach to it and what you can do with it. The other big difference is the fact that we now have an org-wide network as well as org VDC-based networks. So you can now create org networks that are restricted to within a VDC, as opposed to the current version of VCD, which allows you to create org networks that span all the VDCs. So another cool feature that has come out is that now we've bundled network security in terms of the edge firewall. I'm getting ahead of myself here. The edge firewall has been upgraded to hardware version 7, which is what gives it the capability of having up to 10 interfaces. You can either deploy it as a minimal configuration or as a full configuration. The distinction between the compact and the full is the amount of throughput and the capabilities that it has. In compact mode, you can think of it as having an aggregate throughput of about 1.6 gigabits. In full version, it will go up to about 9 gigabits of throughput. If you deploy your network with a compact version of the vShield Edge, you can do a live migration to a full without having to turn off the network or turn the machines off. The other cool feature that comes with the new vShield Edge is the fact that you can deploy it in an HA configuration. What that does, or what that means, is that you can now have 2 vShield Edges that are running at the same time, one in standby mode and the other one in active mode, and they have synchronous configuration or updates of their configuration synchronously. The other big feature is that they can now do DNS relays. And what that does is, or what that gives it the capability of doing, is caching DNS entries. So the inside network can do DNS queries directly to the vShield Edge. The vShield Edge will do the actual DNS lookup. So now you don't have to have reachability of the external network from the internal network, and yet you can still do DHCP or have a centralized DHCP server. The external address space can also be increased on the fly. Originally, you could assign an external IP address to the vShield edge. Once that was assigned, you are stuck with it. Now you can increase that on the fly by adding more IP addressing spaces. And those IP address spaces do not have to be contiguous. And they do not even need to be in the same Class C or Class B network. The ability to sub-allocate IP addresses to the org VDCs or to the organizational virtual data centers is also new. And what that allows you to do is take a block of IP addresses that are assigned to a vShield edge, and then take the different organizations that are, or organizational VDCs that are behind that vShield edge, and assign sub-allocated IP addresses from it. That gives you a finer granularity when it comes to managing of the IP address space that is external to the vShield edge. Organizational networks, like I said, now come in two different flavors: standard org networks and org VDC networks. The org network by itself is contained wholly within the VDC, and it provides connectivity for the VApps in the organizational VDCs. An example of this would be a network that is specific to finance. So if you create two organizational VDCs, say one is called finance and the other is HR, you can create networks that are specific to the finance network and networks that are specific to HR. When you deploy virtual machines in either one of those VDCs, the only networks that they'll have visibility to are the ones that are specific to the org VDC. Remember, originally when you created an org network, the network was available to all the VDCs within that network. So you could not isolate networking to specific organizational VDCs. The standard organizational VDC network now is the one that spans all the VDCs within an organization. And it gives you the capability of providing connectivity between different org VDCs to the same network, so that you can have VMs in separate org VDCs, but they can still share the same layer 2 network. An example of this would be a network connection to the internet. You only want to have one internet connection to the external network, and that will be provided to all the organizational VDCs. So the new network pool that was created with the release of 5.1 is VXLAN, and this is an IETF draft standard that has been put out by multiple vendors, including VMware, Cisco, Broadcom, Arista, and a whole bunch of other people. And I'll talk a bit more about that later. Another cool feature that has come out is more for the benefit of our partners as well as our customers, from the point of view that they can now consume the networks that they're used to and the services that they currently use, or vendor services that they like. What it does is it gives a framework for insertion of third-party services as well as VMware-based services. You can think of this as having ability to load balancers from other parties like, say, F5, or having network services like IDS from IDS providers. You can load those and make extensions of them so that they're now available to your tenants. The profiles are created on these services, and those profiles are the ones that are applied to either the DV port groups or to the virtual wires. And the virtual wires, in this case, you can think of as virtual layer 2 networks that are available within VCD. So when it comes to providing or provisioning these organizational VDC services, the first thing you do is obviously you create your organizational VDC. You then go into the properties from the GUI for vCloud Director. Within that particular VDC, you would go into the properties of it, and you'd have all the networking services that are extensions for it. If I had some within my environment, you would have seen third-party services. These would be extensions of the networking, things like load balancers and IDSs. And then you'd have, things like IDSs and other networking switches. And within the edge services are places where you'd have things like load balancers or VPN services that would be provided by third parties. So once you've enabled it, it takes one click to deploy a network, and those services are an option to the tenant. So if you have, say, a load balancer from F5 inserted and made available as a service, when a tenant deploys a network, they will now have a choice of what kind of load balancing services they can use. As an overview, when the org VDC is created, you now have that software-defined virtual data center that you have. It comes with a collection of networking tools that are available, or networking services that are available to you. You would then create networks, and those networks would pull in those services that were made available in the networking. And then when you created a virtual machine and attached it to those networks, it would rely on a tap into the network to provide the services that are extended into the organizational VDC. So the tap concept is kind of new in this case, and that's the way we'll be inserting the services and associating the virtual machine networking with it. So when it comes to edge services, on the other hand, when an org VDC is created, those services get selected at that point. And then when you create or deploy an edge, those services come with a new edge. And now when you activate them by connecting networks to that edge, you now have the capability of consuming the new services that have been made available, and services that are going to be inserted into the edge, like I said, are things like load balancers, VPNs, and the rest. So let's do a deep dive into the networking. And before we start, any particular questions on the refresher and the deep dive that I gave? Okay. I know I'm the last presenter before you head off and get ready for the party, so I'll try and be quick for you. So vCloud networking and security, new bundle that has come out. And what it includes is vShield app, the Edge firewall, as well as VXLAN. It does not include the vShield endpoint because that is now being integrated, or at least as of the writings of these slides, has now been integrated into vShield or vSphere 5.1. The bundle comes in two flavors. It's either a standard bundle or an enterprise bundle. And the standard bundle, I believe, is what you'll get when you get your vCloud Director licenses. And that will include VXLAN, NATing capabilities in the vShield Edge, DHCP, as well as the Edge services themselves. It will come with a VPN and whatever services that you'll be able to plug in from the ecosystem. And those are service insertion services from third parties as well as VMware. If you do get the enterprise version, it adds on the load balancing as well as the HA capabilities for the vShield Edge. If you are to look at the DHCP that's provided by the vShield Edge, it is now available even on isolated networks. Previously, when you deployed an isolated network, you didn't get any of those services, and you had to deploy a VM within that network to provide them for you. Now, when you deploy an isolated network, it comes with an edge to provide services like DHCP for you. It doesn't provide anything else that requires external connectivity like VPN because there is no external interface associated with it. The DHCP that's provided only has standard, doesn't have all the standard DHCP options. The only thing that you can actually do is assign IP addressing and configure the lease times that are associated with those addresses. The other shortcoming of it or limitation of it is the fact that you can only have a single pool of IP addresses per interface. In other words, you can't have multiple subnets that are on the same interface unless you have your own DHCP server that's assigning them or you have static IP addressing on the virtual machines that you have. NAT is the other service that's provided, and these rules are applied on a per interface basis. Remember now you have multiple interfaces. You have NAT rules that are specific to each one of those interfaces. The rules can now be arranged in the GUI, and this is the GUI interface that you're going to see, and you can click on an interface and drag it to rearrange the precedence of those NAT rules. And the NAT rules are processed top-down. You can have DNAT support now for THCP, UDP, as well as TCP and UDP. And we've added ICMP and the capability of having NAT rules for anything that comes in. Source and NAT rules, we now have source DNAT and DNAT rules, as well as a bunch of predefined ICMP types. So the idea is you can create NAT rules for specific ICMP rules as well. This is the interface that you have for your DNAT rules, and this is the interface that you have for your source NAT rules. In source NAT, it's pretty simple because you're just taking your internal IP address and mapping it to an external IP address. Originally, you didn't have the capability of doing source NAT because every outgoing address just utilized the external interface of the vShield Edge. In the DNAT rule, you have now your protocol selection as well as your inbound and outbound ports. And if you are selecting ICMP for your protocol, then you could use the drop-down to pick up any of the ICMP types that are supported. For the firewall, it's a 5-tuple firewall. And when we say 5-tuple, it means, or we are talking about the fact that you are dealing with a source IP address as the first tuple. the destination or the source port, a destination address, a destination port, as well as the protocol. That's what makes it a 5-tuple rule. The rules like the NAT can also be arranged using drag and drop now within the interface. The default action is deny, which means the last rule in your firewall rules, you think of it as IP tables, in the last rule of the IP tables of the firewall are the drop rules. If you set it up to allow, then the last rule is allow any, and what you'll have to have is negative rules in your firewall. The firewall also supports TCP rules, UDP rules, a combination of TCP and UDP, ICMP, and any. The distinction between the NAT rules and the firewall rules is that we don't have any filtering on ICMP type. So I can't create a rule that says specifically allow ping out, but don't allow trace route out. The address range for the source and destination can now be classful. So I can go in and say, I'm entering a rule for the whole class C, as opposed to having to put a range of IP addresses. The other big difference is static routing. And static routing is great now because when you have multiple interfaces on a vShield edge, you don't just have ingress and egress traffic. You now have traffic that goes to multiple interfaces. The example I'm showing you here is creating 2 different org VDCs within the same organization. And within one of the org VDCs is an application that you might want to get to. On this side, looking at it from the configuration for this vShield edge, it says to get to the network 1.0, which is over here. The next hop would be the 10.100, 10.1.10 interface, which would be this vShield edge's outside interface. And to get to all the other networks, you'd do the same thing. The special one is this 171.120 network, which is the vApp network that you want to get to. Once it comes to this interface, this vShield edge has a static route for it that says to get to it, you have to go to this other vShield edge, which is in here. So now you can come in all the way from this particular blue network, traverse through your vShield edge, go through an org network, and get routed all the way through to the internal network of a vApp. So this gives you a lot of capabilities in terms of having internal organizational-based routing capabilities that we didn't have before. It is currently limited to just static routing, but I'm sure down the road we'll implement some forms of dynamic routing for you. VPN capabilities now, site-to-site VPN. The VPN that's built into the vShield edge is not an access, is not for individual access, but a site-to-site VPN. And what that means is that it doesn't do bridging in any way, but actually requires different IP subnets on the 2 different ends of it. It now supports an SSL VPN on top of the IPsec VPN that it did before. And it is compatible with a whole bunch of different hardware vendors as well as software vendors out there. The load balancer now does a bit more than what it used to be. For starters, in the original version, the load balancer was only available through the virtual center interface. So that once you created a network, you could now jump into the virtual center interface and create or configure the load balancer that was associated with that network. So you didn't have any capabilities of configuring it from within your vCloud Director environment. Now that interface has been brought into vCloud Director, and a tenant, when they deploy a network, can add load balancing functionality to it. Originally, it could only load balance HTTP, but now it load balances HTTP, HTTPS, as well as arbitrary TCP ports. That gives you the capability of load balancing any type of application that you have, not just web servers. You can add a health check URL that goes to any arbitrary monitor port that you have the capability of. It gives you the capability of testing out your application for total health from end to end before you allow access to your application. The way it's configured is 2 different aspects of it. You have your pool servers, and the pool servers are the virtual machines on the back end that actually do the work for you. The virtual server is the outside interface IP that would be mapped to the load balancer outside IP to load balance the application that you have. If we look at the load balancer pool server configuration, they load balance both HTTP, HTTPS, and TCP. And like I said, the health check URL can use any arbitrary method. What you need to get out of this is that The load balancing methods can be used for all protocols except the URI does not work for HTTPS currently. For the virtual server, think of it as what we standardly know as a VIP or the virtual IP. This is the IP address that would usually be entered into DNS to give you access to the application that you're trying to get to. For HTTP persistence, it uses cookies with insert. For HTTPS persistent, it can use session IDs now. There is no persistence method for standard TCP, mainly because we have no idea about the protocol that's running inside some arbitrary TCP port. Before you can configure a virtual server, you have to have your server pool available, as well as an IP address to be assigned to a specific interface that you're going to apply the load balancing to. So if we look at different network pools now, if you look at the pod group backed one, what it requires is any kind of virtual switch that we have, so it'll work on a VSS or a DVS. How you configure it is pretty much standard VI work. You just go in and create a pod group within Virtual Center and then apply that as an external, as a pod group as a network pool to vCloud Director. The advantage of pod group backed network pools is the fact that you can pick any arbitrary isolation method that you want. You can either have isolated switches that are used for it, you can have VLAN tagging for them, or you can use any other isolation scheme that you have within your physical environment. The biggest disadvantage to it, obviously, is the fact that you're now at the mercy of your VI administrator, meaning if they make mistakes in terms of isolating those pod groups, you have no way of knowing that or seeing that from within vCloud Director. So you should make sure that when you're using pod group backed networks, that they're actually isolated in some way, or when you verify it within the VI, you make sure that they actually have some form of isolation like VLAN IDs that are unique to each one of them. The idea being that when you take these pod groups and you apply them to network pools, when you assign networks to a tenant, you have no way of ensuring that they're isolated from each other unless the pod groups are isolated in some way. They work regardless of the isolation scheme. And if you're using a VSS, the only thing you need to be aware of is that it does require manual work up front. And if you have multiple ESX servers within a cluster, then orchestration would be needed. Otherwise, it's just a lot of work. For VLAN-backed network pools, they only work with distributed switches, and you do need a pool of VLAN IDs that you'll assign to them. These pools will be assigned to a configuration during your VCD setup. How it works is that VCD will create the pod group within your virtual infrastructure on the DVS that you designate, and it will apply one of those VLANs from the pool to that pod group that you created for isolation. So depending on how many VLAN IDs you assign to the pool, that will be the limitation as to how many networks vCloud Director can create using that pool. The advantage of VLAN-backed pools, obviously, is the fact that the isolation method is well understood, and we know how to mitigate risk with it within the networking environment. And it's supported pretty much by all enterprise-class switches. The biggest disadvantage, as far as I'm concerned, is the fact that VLANs are in limited supply. So most of the times, you won't have an infinite supply of these, and when you're thinking about it from a cloud deployment, you want to have as many virtual networks as you possibly can, and your tenants will consume these as fast as they can. So having a limited commodity like VLANs makes it a little more difficult for you to have a scalable environment. The other disadvantage, I think, is the fact that that VLAN needs to be available on all the trunks on all the cluster-based ESX servers that are participating within your vCloud environment. And if one of those trunks is not configured correctly, then you'll have funky disconnects on virtual machines as there vMotion between hosts. So it just becomes a little more difficult to troubleshoot. The other disadvantage, obviously, is that they're restricted to a single VDS and a single virtual center. So you can't create VLAN-backed networks that span multiple vCenters or multiple VDSs. For the VCDNI-backed network pools, though, it does require a distributed switch. And how it works is that VCD goes through and creates the pod groups, assigns the transport VLAN to that pod group, and then uses a fence ID internal to VCD to create the isolated networks on them. The encapsulation that's used is a proprietary VMware Mac-in-Mac encapsulation. The advantage of using VCDNI over the other pool size is the fact that it doesn't require VLAN IDs for this isolation. The disadvantage of it, and as far as I'm concerned, it's the biggest disadvantage of VCDNI, is the fact that it shares a common broadcast layer for all the isolated networks. And what that means is that if you have isolated networks and they do broadcasts, those broadcasts are visible within each one of those, within all the other VCDNI isolated networks. It does share the same transport network, and when you're configuring VCDNI, you need to assign it a VLAN ID for the transport network, and you also need to ensure that it's a free VLAN that's not used within the environment and that it's non-routable, because the encapsulation is nothing unique, and it's easy enough for you to insert packets into the network as required. It's also restricted to a single VDS and a single vCenter. The fourth type of networking pool is the VXLAN-backed one, but that does require more than one page to explain, so we'll go into a few more details of VXLAN. Any questions before I go down the route of VXLAN? Okay. So this is a new type of networking pool. And what it allows you to do is create overlay networks over your network. So you have multiple layer 3 networks within your data center. If you want virtual machines to be available all over your data center, you need to be able to have them on the same layer 2 network. In other words, they need to be able to talk to each other on the same IP subnet. So VXLAN allows you to overlay a layer 2 network over multiple layer 3 environments. It relies on a segment ID, which is a 24-bit ID, and that's known as a VNI, or VXLAN Network Identifier. And the fact that it's 24-bit gives you the capability of creating about 16 million networks. The traffic between hosts is encapsulated in a tunnel between VTEPs, or what we call VXLAN tunnel endpoints. And the VMs that are participating in the VXLAN network are definitely not aware of the fact that they are being transported across a VXLAN tunnel. VM to VM traffic is all encapsulated into a VXLAN header and a VXLAN and transported over the tunnel unless the VMs are on the same port group and they're communicating to each other. Multicast is used for all the broadcasts from the VMs as well as any unknown traffic that the VMs are producing. What that means is that you can now go in, create a VM, run things like IPX or NetBEUI if that's what you want to run, and that packet will be encapsulated into the multicast packet and transmitted to all the VTEPs within the environment to be delivered to the destination VM. So it gives you a lot more flexibility in terms of what you can run across your data center from a VM point of view. What it does require is a distributed virtual switch. It won't work with a VSS. And it will also require an available VNIC and an IP address per switch or per VLAN that is going to be used for. And multicast addresses if your VTEPs are going to live on separate layer 3 networks. How it works is that VXLAN creates a network, gives it a segment ID, and maps that to a multicast ID or a multicast IP address that's available. The VM traffic is tunneled between two endpoints, and the two endpoints are usually ESX servers, or if you're running a Nexus switch, a Nexus N1K V. All learning within the network is done using multicast flooding, meaning that if a VTEP needs to deliver a packet to a virtual machine and it doesn't know what VTEP is the destination, it'll do a multicast flood to all the multicast-enabled VTEPs within that environment. And only the VTEPs that are participating in a particular network segment will receive those packets and process them. Advantage of it all is the fact that we no longer rely on VLAN IDs for isolation. We also work on any multicast-enabled network. One disadvantage is we do require multicasting if you are going to be spanning multiple layer 3 networks, and we do need an increase in MTU to 1600 at a minimum. Some details involved around VXLAN. Within VMware, and by the way, I won't be talking about specific implementation details on the Nexus switch. I'll only be talking about VMware implementation or how we've put together the VXLAN environment. So how it's implemented is as a VM kernel module. The multicast radius is what determines the limit or the stretch or how far your VXLAN network can go. So if you want to limit to within one data center, you will limit the propagation of those multicast addresses past your gateway routers or your border routers. Multicast is used for encapsulation, like I said, of all unknown traffic, including broadcasts. So what that does for you is it limits the amount of broadcast traffic that your core switches or your distribution switches will have to deal with. It does make good use of ECMP for cases where you have multiple paths through the network. Broadcasts from a VM, multicast from a VM, or unicast packets that are to unknown destinations will all be taken and encapsulated and transported over multicasts. The multicast group can be allocated to a VXLAN segment, and you have unique within a specific namespace, and a namespace in this case would be one organization or a combination of Virtual Center and vShield Edge. So within a particular namespace, you will have specific VXLAN segment IDs that will be designated to them. Those have to be unique within your implementation. But the multicast addresses that those VNIs will use does not need to be unique. The combination of multicast and VNI is unique. So you can have, say, 10,000 VNIs that are associated with a particular implementation, but only, say, 10 multicast addresses. And we'll cycle through those multicast addresses and use the least used ones. IP management for the VTEPs itself leverages the DHCP and VM kernel stack that already exists. IP address allocation for them relies on DHCP. And what that means is when you create a VTEP, the first thing it does is it does a broadcast request for a DHCP address. If the network is not DHCP enabled, then it just requires you to cycle back to the VM kernel NIC and assign it as IP address on the layer 3 network that it's on. It does leverage the VM kernel TCP/IP stack for all the IGMP processing that needs to get done. VXLAN, because it's UDP-based or transported over UDP, and the fact that it will make good use of ECMP, makes very good use of multi-link connections within your network. UDP source port entropy, which is used for picking the path that will eventually get used in a multipath environment, exploits or makes good use of ECMP. And the entropy for those source ports is based on the inside MAC address of the packet, meaning the MAC addresses of the destination and source VMs is what's used to generate the source port, or the source ports for UDP entropy. As an overview, the VDS configuration is all handled for you by the vShield manager during the Fabric setup, and I'll walk through the UI of how the Fabric is set up for you in a little while here, as well as the MTU increase to 1600. So when you go through and you're setting up the Fabric, you'll have options to set all these things up, and they'll get pushed out to the VDSs that you designate for you. In terms of the physical switch configuration, the one big change you'll need to make is MTU needs to be increased to match whatever you set up in the VDS. IGMP snooping needs to be enabled on the physical switches. And just as a quick poll for the crowd, how many of you are actually running multicasting within your environment? Wow, a lot more than I usually expect. So to be able to run multicasting within an environment, you need a couple of things. And some of those things are IGMP snooping on the switches themselves, as well as an IGMP query. The IGMP query is the one that sends out packets saying, hey, who's doing multicasting and what networks, or what groups do you belong to? The endpoints will respond with the groups that they belong to. The switches, if they're running IGMP snooping, will see those packets, and they'll figure out what multicast groups each one of those individual ports is listening to. So when multicast packets come through, the switch will filter them and only send multicast traffic down to the ports that require the traffic. So IGMP snooping needs to be enabled, and the IGMP query, which is usually a router, needs to be turned on. But if you have layer 3 switching, you can also run an IGMP query on those. We do need PIM multicast routing, because that's how we get our multicast traffic across layer 3. And if possible, bidirectional PIM is what you should enable on your routers or your routing modules. The reason we require bidirectional is because our VTEPs are not receiving multicast traffic only. They're also sending multicast traffic, so bidirectional PIM is required or suggested. You can use PIM single sparse mode, but it just makes it less efficient. So let's walk through the setup of the fabric itself. Within Virtual Center, you have an option now to configure the VXLAN network virtualization. And the first thing you need to do is configure the segment IDs. The example I'm giving you here is that you start off from VNI 5000 through 6000. And what that gives you the capability of doing is creating up to 1,000 VXLAN-backed networks. If your goal is to create about 10,000 networks, which would be the case usually with a vCloud implementation, then you need to ensure that you have 10,000 VNIs set aside. You also need to associate or get multicast IP addressing from your networking folks that are applied or available within your network that you can apply or use for your VXLAN network. Once you've done that, the next thing you need to do is associate your clusters of ESX servers with DVSs that will be used for creating all your VXLAN-backed pools. The other thing you need to do is assign a VLAN ID for each one of those uplinks that you're going to be using. The VLAN ID is the transport VLAN for your VTEP if you have one. Once you've done that, you need to modify the NIC teaming policy for the port group that will be created for carrying all your VXLAN traffic. By default, it defaults to static Ether channel. And the reason for that is we do not support non-trunked or non-teamed NICs when you have multiple NICs on a DVS. So if you have more than one physical NIC going into a DVS, it has to be channeled in some way. You can either use static Ether channel, you can use active LACP, or you can use passive mode LACP for that. This is also where you can increase the MTU for your VDS. Once that's all done, then a whole bunch of things happen between Virtual Center, the vShield Manager, and the ESX servers. One of the big ones is that we push out a VIB, which is a binary that goes into the ESX servers for the vShield Manager. We then configure a virtual NIC on each ESX server that will be used as the VTEP endpoint. If you look at the network virtualization tab for your particular data center, you will notice that each one of the clusters that you configure goes into a waiting mode while all these other things are happening in the background. When everything is done, each one of your members will show ready, and it'll have an IP address assigned to each one of the VM kernels that will be used as your VTEP. If you look at the distributed switch that you chose to carry your VXLAN traffic on, it'll now have a VM kernel port associated with it with an IP address assigned. And this is where you'd also come in and do and manage virtual adapters and change the IP address if you require a different IP address or if you change your layer 3 networking. So a few questions like, why would you use VXLAN? Why go to the trouble of doing all the things that I talked about, like increasing multicast, increasing MTU on your physical switches, adding multicast to your network? Well, the biggest one from a vCloud Director point of view is the fact that it gives you immense amounts of flexibility in terms of the kind of networks that you can create, where you can deploy your virtual machines, and where you can actually place your ESX servers to belong to the same cluster. It allows you to do on-demand provisioning of isolated networks. This means that within vCloud Director, you can now start creating networks without having to make any changes to your physical environment. Like I said earlier on, the 24-bit segment ID gives you the capability of creating 2 to the power of 24 networks, which amounts to about 16 million networks. You can create layer 2 overlay networks all over your data center. So long as you have multicast enabled within your network, you can create ESX servers anywhere in your data center and have them belong to the same cluster, because unlike previously when you had to have the same visibility of networking from your ESX servers, now because we are enabling VXLAN as an overlay network, you no longer have to have your ESX servers living or having the same visibility to network. For me, the biggest reason to implement VXLAN is the fact that you avoid STP altogether. You don't have STP convergence issues because now you're having very little change within your networking environment from a physical networking point of view. You also don't have to use VLANs. The other big thing that you're going to notice when you start using VXLAN as an overlay network is the fact that your switches are going to have a lot less MAC addresses in their CAM tables to deal with. And the reason for that is the only MAC addresses your physical switches see are the MAC addresses of your VTEPs. All the VM to VM traffic is all encapsulated within the tunnel that is coming from or between the VTEPs. So you also have a lot less broadcast traffic that your physical switches need to handle, because that's all encapsulated as multicast traffic, which your switches handle a lot more efficiently. So the consumption model, or how you would consume VXLAN within the environment, is you'd first have to enable the virtual infrastructure. And I walked you through the fabric setup that we did. What you need to do is VDS configurations, uplink managements, managing your QoS if you have QoS requirements within the environment, and configuring your physical switches, so setting up your VLANs, your ACLs, and your QoS throughput as well. Once you've configured the fabric or the physical environment, you can now overlay and create your compute scope networking. And what that means is now you can create your VXLAN network pools. And once you've got your VXLAN network pools, you can now start creating virtual wires, meaning virtual layer 2 networks that span your data center and start consuming your VXLAN. From a VCD point of view, you'd usually end up having multiple VDSs in a VCD environment. You would overlay the VXLAN fabric on top of that. You would then create your provider VDCs. Once you've created your provider VDCs, you'd start allocating organizational VDCs at that point. And as you create the organizational VDCs, you'll assign a vShield edge associated with it and be able to create networks behind it. You would then create virtual wires for your VXLAN. And then as you add more capacity to your provider VDC, say you're adding more clusters to your VDC so that you can expand your provider VDC, those virtual wires get transposed and created on the new ESX servers that you just added. If you are to create more organizational VDCs, the virtual wires will also be expanded to include the new organizational VDCs that you are adding. And the configurations are all available through REST API, like everything else within VCD. If we are to look at a physical view of how all this works, these are two ESX servers that are being represented by my black boxes. I have two VMs that need to communicate with each other. The assumption is that they are on the same pod group, on the same DVS called pod group 192.168.1. And that pod group is available on a DVS, so it's visible to both ESX servers. There's a VTEP associated with a VDS, and there's also a gateway that gives you capabilities of getting out of your VXLAN-backed pod group and out to, say, a VLAN-backed pod group that is associated with your internet connection. So when the VMs communicate with each other, the packet goes out through their pod group, is captured by the VTEP. The VTEP tunnels it across the physical network and then decapsulates the packet, dumps it on the pod group, and then makes it available to the VM. If the VM needs to talk to the internet, it goes through its pod group to the inside interface of the vShield edge. Remember, there's no VXLAN that happens over there. The gateway takes that packet, dumps it on the external interface, and makes it available to the rest of the internet. So the packet structure for the encapsulation, and if you've been to one of my previous demonstrations, you've noticed that I used the same slides that I had last time. You start off with the original L2 frame that comes from the VM. We add on a VXLAN header, and the main important thing in the VXLAN header is the fact that we now tack in a VNI, and that's 24 bits. There's a whole bunch of reserved fields in there for future use of VXLAN. Once you've done that, you add on a UDP header, and that UDP header, the important thing to note is that it has a VXLAN port as the destination port, and we are currently using the 8472, and if you know what that is, it's also the same port that's used by OTV. For the checksum, standard utilization says that you set that to 0, all zeros. If the checksum is not all zeros, then it tells the VTEP that if it does check the checksum of the packet, if it doesn't compute, then the packet needs to be discarded. But there's no requirement that it has to be checked by the VTEP just because the checksum is 0. It just means that if the checksum is non-zero, if the checksum doesn't match, then the packet has to be discarded. We then tack on an outer IP header, And the thing to note about the outer IP header, or the important part over there, is that the source and destination IP addresses match the source and destination VTEPs associated with the tunnel. We then put on a MAC address header on it, and the major thing about it is the fact that the destination address is the next hop, usually the next hop router, and the source MAC address is the MAC address of the VTEP itself. If you're using a transport network or a transport VLAN for your VXLAN tunnel, that will be added in as an optional amount of data within the packet itself. All of this adds up to about 50 bytes, which is why we ask you to extend the MTU to 1600. Okay. Any questions before I walk you through a packet flow through the network?
For VXLAN implementations where you have seen customers put this in, what are the biggest operational challenges that have they faced? You mentioned some configuration issues such as enabling MCAST, but how about operationally?
So operationally, or customers that have deployed VXLAN, I would say there's nothing publicly out there yet, because this is a product that's going to be GAing soon. But from our experience, the biggest thing or the biggest issue that we've seen or we've come across is usually the resistance to increase the MTU within the physical network.
Okay, but that's still configuration.
Yeah, it's still configuration. Operationally, what it does for you is it gives you that capability, like I was saying previously, of putting your ESX servers that will belong to the same cluster anywhere within your data center. So from an operation point of view, you don't have to you don't have to restrict your thinking to say, all my ESX servers within a cluster have to be on a specific row in the data center, because that's where those VLANs are available.
Thank you.
Okay. So if you look at an environment where you have the two ESX servers that we were talking about, or I showed you before, talking to each other, you can think of them as sharing an L2, that is your VNI 864. There is also a full-blown network on the back end that is all physical. If the VM wanted to communicate from VM1 to VM2, it would first start off with its original packet with all the information that it usually has, its source MAC address, the destination MAC address of the VM, IP address of the origination, and the destination IP address. The VTEP takes that packet and tacks on the VXLAN header to it, puts on the UDP header and an IP header. And like I said, the source and destination IP address will be the source IP address of the VTEP and the destination IP address of the remote VTEP. Once it tacks on the MAC address header, the MAC address will be the source MAC address of the VTEP itself. The destination MAC address will be the next hop, which would be its router or its default router. The packet will traverse through the network, changing the MAC address header every time. But once it gets to the remote side, the VTEP will strip off the MAC header and all the other headers associated with it and pass the original packet to the destination VM itself. Okay? And that picture, it works exactly the same for multicasting when it's unknown traffic, because the VTEP will encapsulate the multicast traffic. But in this case, instead of encapsulating it as a destination of the VTEP IP address, the destination will be the multicast group that the packet belongs to. And it will traverse the network in exactly the same way. Yes?
How do the VTEPs learn where those VMs exist? What process is used to learn?
The learning requires multicasting. So take an example of the case where this VTEP has no idea that this VM lives on VTEP 2. The first thing it will do is it will take the app address, say this machine was sending out an app request. It will take that original app request, wrap it up in the same encapsulation method that we talked about. The destination IP address would not be the VTEP because it doesn't know that IP address. It will actually be the multicast IP address associated with the multicast group. All the VTEPs that participate in that multicast group will receive that packet. They will decapsulate it, see it's an app request, and forward it to their network. But in the process, what they will learn from the packet would be the source IP address of the VM, this VM, and the source IP address of the VTEP. So all the VTEPs that are participating in that multicast group will add to their tables the source IP address of the VM as well as the source VTEP, because now they've made that association. so that if they ever need to talk to that VM again, they know what VTEP to send the packet to. When the packet goes to the VM and the VM sees the app request, the VM that is responsible for that MAC address will now respond, and the VTEP will take the response that says, hey, that MAC address belongs to IP address me. The VTEP will now take that will now take that packet and will not encapsulate it in a multicast address because now it knows where that VM lives. It will encapsulate it in a unicast packet, and it will work exactly the way I was describing previously. So all learning is done through multicast flooding to the multicast group that the VNI belongs to.
I have a follow-up question. How is, if those VMs move around, is there an aging process or something that expires?
So the standard way that we handle things like vMotion is when a VM moves from one host to the other, the VM kernel sends out a gratuitous app to the network. That gratuitous app is encapsulated as a multicast packet and distributed to all the VTEPs. Any other questions? Because this is the last slide, by the way. So feel free to ask as many questions as you like. These were other VXLAN kind of based presentations that are available, including breakout sessions and some group discussions. Some of them might have already expired, like the group discussion I know happened today morning. All right. I'll be available for a while. I'm the last presenter here, so I have as much time as you need.